Welcome back, everybody. This is our second session in JEemains previous year videos for chapter Nuclei. Now, before this video, there is one video available on our channel's playlist section for this chapter. And find this video useful, then do press the like button, share it, subscribe to our channel, like to donate us something, scan the QR code. With this, let's start today's video. In the previous one, I think we covered up to question number 10 or something. Yeah, this was the last question. Now we will start with the next one. Imagine that a reactor converts all of mass into energy and it operates at a power level of 10 raised to power 9 volts. The mass of the fuel consumed per hour in the reactor will be velocity of light is given to us. So uh, the reactor is operating at a power level of 10 raised to power 9 volt. So it is basically 10 raised to power 9 joule per second. So reactor is producing 10 raised to power 9 joules per second, and we have to calculate fuel consumed per hour. So the energy produced by the reactor in an hour, that will be equal to 10 raised to power 9 into number of seconds in an hour. So that is basically equals to 3.6 into 10 raised to power, I think 12 joules. So this is the amount of energy that is produced in an hour. Now, from this, what we can do, we can calculate the amount of mass that will be converted into energy. We know that delta E will be equal to mc square. So from this, m will be delta E, that is 3.6 10 raised to power 12 divided by c square, that will be 9 into 10 raised to power 16. So that will be 0.4 into 10 raised to power minus 4, or 4 into 10 raised to power minus 5 kilogram. Now answer is in grams, so that will be equal to 4 into 10 raised to power minus 5 into 10 raised to power 3 grams. That will be 4 into 10 raised to power minus 2 grams. So option C is the right answer here. Now let's move to the next one. Two neutrons undergo nuclear fusion to form a helium nucleus. Energy released in the process given binding energy per nucleon for deuteron and for helium. So basically what we have two deuterons. So deuteron is 2H1 plus 2H1, and they give rise to 4He2. Let's assume this reaction is possible. So we have to calculate energy released. So for that, delta E will be equal to the total energy of the daughter minus total energy of the parent. This will be the energy released. If we take total energy of parent minus total energy of daughter, that will be the energy required. So that will be 4, and for helium it is 7. Helium has 4 nucleons, and each nucleon has 7 MeV binding energy per nucleon minus twice 2 into 1.1. So that will be 28 minus 4.4 and basically 23.6 MeV. So option C is the right answer here. When uranium is bombarded with neutrons, it undergoes fission. The fission reaction is given by this reaction, where 3 particles named as 3x are produced and Q is released, the name of the particle X. So if I match, or if I balance the mass number, then what we will get from the left side, I will get 235 plus 1, and from right side I will get 141 plus 92, and 3 times x. So from this, if we solve this, I will get x is equal to 1. So this is basically mass number. Coming to the charge, so 92 plus 0 is 56 plus 36 plus 3x again, and this will just, from this, x is 0, and let's mark it as x dash. So x dash is 0. So Our element, this unknown element X, has a mass of 1 and charge of 0, and that is basically a neutron. So neutron is the right answer here. So option C. Assume that neutron breaks into proton and an electron. The energy released during the process is. So it is mentioned that a neutron breaks into a proton plus a electron, and we have to find out the energy release. So basically the energy release will be mc square delta mc square. Now we by default know that here it is already also mentioned that mass of neutron is 1.6725 and mass of proton is also 1.6725. So here on the right hand side we have proton plus electron. Now electron has additional mass also, so we can say mass of parent here is less than mass of daughter nucleus, because proton and neutron have the same mass, and on the right hand side we have additional electrons. So mass of right hand side is greater and mass of left hand side is smaller. So mass of daughter is greater than parent. So this reaction is not possible, by itself. So to make it possible, what we have to do? We have to provide energy. So the energy provided will be equal to delta mc square. Now mass difference here is the just equal to the mass of electron, that is 9 into 10 raised to power minus 31 into c square, that is 9 into 10 raised to power 16. So this will be 81 into 10 raised to power minus 15 joules. Now we need to convert it into electron volt. And if you remember that if we convert electrons mass into energy, what we get? We just get 5.11 MeV. So that is the energy required. We can also convert it by dividing 1.6 into 10 raised to power minus 19. So from this I will get 50.625 into 10 raised to power minus 4. Now I have to convert it into MeV, mega electron volt. So it's just electron volt. So, oh sorry, this will be plus 4. So I can write 0.50625 into 10 raised to power 6 eV, and this is basically 0.51 MeV. So either you can use shortcut that to produce an electron we need 0.51 MeV. So that will be the answer, or you can just calculate. So option A is the right answer here. Now in the next one, we have ionization energy of lithium atom in the ground state is 5.4 electron volt. Binding energy of lithium positive ion in the ground state is 75.6 electron volt. Energy required to remove all 3 electrons of the lithium atom is. So we have a lithium atom, and this lithium atom has 3 electrons. So to completely ionize this lithium atom, what we have to do? First, we will remove 1 electron, and then it will become 7 lithium, and it will stay as 3 positive. Then we will remove other electron, then it will become 7 3 lithium 2 positive, and then we will remove another electron. So this will become 7 lithium 3 positive. Now if you analyze carefully, at this state lithium has 3 electrons. Here lithium has 3 electrons. So if we remove the 1 electron, what will be the amount of energy needed? Here lithium is in ground state and amount of energy needed will be 5.4 electron volt. So to remove the 1 electron, when lithium has 3 electrons, we need 5.4 electron volt. Now at this state lithium has 2 electrons because 1 we have already removed. Now it become lithium positive ion. So now to remove 1 electron from the lithium positive's ground state, we need 75.6 electron volt energy. So now after removing one additional electron, what we have? We have one electron for lithium atom with lithium atom. So now it will behave like hydrogen like element. We have already discussed it in the previous chapter of the in the atoms part. So for hydrogen like element, the ionization energy is basically minus 13.6 into z square by n square. To remove the electron from the ground state, it will be minus 13.6 z. For atomic number for lithium is 3 square divided by the from the ground state, that is 1. So that will be the amount of required energy will be 122.4. So here we will need 122.4. So total energy needed will be 5.4 plus 75.6 plus 122.4, and it is to 203.4 electron volt. So option C is the right answer here. Now let's move to the next one. After absorbing a slowly moving neutron of mass mn, momentum almost zero, a nuclear mass m breaks into two masses of m1 and 5m1. 6m1 is equal to capital M plus small n respectively. If de Broglie wavelength of the nucleus of mass m1 is lambda, the de Broglie wavelength of the nucleus will be. So basically what we have a capital mass M nucleus, and it absorbs a neutron of mass small n, and what we will get, we get two masses, a mass m1 and another mass 5m1, and the relation is which is given to us that 6m1 is equal to basically its mass conservation mn. Now as already mentioned that after absorbing slowly moving neutron, so momentum of neutron is given to be 0, and this nucleus is absorbing the neutron. So we assume, and normally its momentum is also taken as 0, means normally what happens in this type of reaction, that target nucleus is always at rest. So its momentum is always 0, and we have some neutron or some radiation striking to it or incidenting on it. And as mentioned here that this neutron also have momentum 0. So we can say total initial momentum is 0, and this should be equal to the momentum of mass m1 plus momentum of mass 5m1. Or I can write that in modulus, momentum of mass m1 will be equal to modulus of momentum of mass 2. So in short, in magnitude, momentum after splitting of m1 and 5m1, the momentums of m1 and 5m1 masses will be equal. And we know that de Broglie wavelength is basically h by p. So if momentums are equal, then de Broglie wavelength will also be equal. And de Broglie wavelength for one is lambda. So for the second one, it will be also lambda. Now, next one. A nucleus of mass m plus delta m is at rest, decay into two daughter nuclei of equal masses m by 2 each other. The speed of light is c. The binding energy per nucleon of the parent nucleus is E1. Then that of daughter nuclei is E2. Then, now as mentioned, that initially parent has mass of m plus delta m, and it decays into two nuclei of equal masses, and each have mass m by 2. So basically we can say mass of daughter is less than mass of parent. So it means mass is lost, and it will be lost in the form of energy. So in this type of scenario where mass is lost in the form of energy, we normally assume that daughter nuclei are more stable. And if daughter nuclei are more stable, then it means that binding energy per nucleon for daughter nuclei is greater than the binding energy per nucleon for the parent nuclei. So that is the basic assumption which we have. Now we don't have any relation that whether how much it will be greater, how many times it will be greater, but we just know that it will be greater. So here binding energy nucleon is for parent it is E1 and for daughter it is E2. So we can safely say that E2 is greater than E1. So option C is the right answer. So now moving to the next one. In a nucleus of mass m plus delta m at rest decay into two daughter of each m by 2 speed of mass, speed of light c, the speed of the daughter nuclei is. So we have to find out speed of the daughter nuclei. Now we know that initially mass is at rest. So we can say initial momentum is 0, and after splitting momentum will be conserved, whether it's elastic, inelastic, or whether any type of collision or explosion it is. So again, momentum will be conserved. So P final should be 0. So one thing we have that both of the nuclei, both of the daughter nuclei will have the same velocities. And let's say that velocity is V. Now what happens here that we have m plus delta m splitting into m by 2 plus m by 2. Now, we know from the previous one also that there is loss of mass, and how much loss of mass is there, that is delta M. So the energy produced delta E will be delta M times C square. Now this energy can be used in various ways, means this energy can be in the form of radiation, in the form of heat, or it can also appear in the form of kinetic energy. Means I can safely say that maximum possible kinetic energy will be delta mc square, or that can be delta mc square if no energy is lost in the form of radiation or heat. So that is maximum kinetic energy. So from that I can say half m v max square is equal to delta mc square, and from this I get v max, the possible maximum velocity, will be equal to, and this will be capital M, sorry, this will be capital M by 2 because mass of, okay, let me write it properly. So as we have two masses, so total kinetic energy will be twice times the energy of one, that will be half into mass of one, that is M by 2, into V max square. So that will be the right relation here. So this 2 cancel this one, and we have V max as 2 delta m c square by capital M whole under root. So this will be c times twice of delta m by m. So option B is the possible answer here, that maximum value, maximum speed will be this one if no energy is lost. Now with this, let's move to the next one. Statement 1. Energy is released when heavy nuclei undergo fission or light nuclei undergo fusion. So that is right. For heavy nuclei, binding energy per nucleon increases with increasing Z, while for light nuclei, it decreases with increasing Z. So we have already, I think, studied it, this binding energy curve. Let me show it. So it looks like something like this. Here on the x-axis we have mass number, that is A, and on the, oh sorry, not mass number, it is basically Z, atomic number. And on the y-axis we have binding energy per nucleon, and the curve looks like this. It looks like something like this. Now this at this is point this is the point of maxima, and this is for iron. After that this curve saturates. So we can say as Z increases for low atomic number, as Z increases for low Z, as Z increases, binding energy per nucleon also increases up to iron. And after that for high Z, high atomic numbers, as Z increases, binding energy per nucleon decreases. So now coming to the statement 2, for heavy nuclei, binding energy per nucleon increases with increasing Z. So that is wrong statement here. So statement 1 is the right answer. 1 is right and 2 is false. So that is option D for us. In the next one, if MO is the mass of oxygen isotope, MP and N are the masses of proton, neutron respectively, the nuclear binding energy of the isotope is. So it will be basically mass difference times the C square. So mass difference here will be. So binding energy will be. Actually, it should be something like this, that here we have how much 17 minus 8, that will be 9. So we have 9 into mass of neutron plus 8 into mass of proton minus mass of oxygen atom. So that, let's say, MO times C square. But here I look it's look like they have interchanged the term. So if they have just taken negative sign, or they have just written it like this: MO minus 9Mn minus 8MP times C square. So it's basically they have taken negative sign common. So in either way, option C is the right answer. Now next one, when lithium nuclei are bombarded with protons and the resultant are beryllium nuclei, the emitted particles will be. So we have 7 lithium 3 plus 1 proton. So proton has a mass number of 1 and atomic Z is also 1. So here if we are getting 8Be4, so if we see here that 7 plus 1 is 8 and 3 plus 1 is 4. So whatever will be emitted, it will be only energy, because suppose I write a let's say neutron here, then this equation will not get satisfied, that 7 plus 1 8, 7 plus 1 is 8 on the right hand side, sorry, on the left hand side, and 8 plus 1 is 9 on the right hand side. So there cannot be any particle, because equation is already satisfied. The only thing which we can have, we can have, that is energy, and energy can be in the form of photons, and the possible answer will be then gamma photons. The next one, if the binding energy per nucleon of lithium, helium are given, then the reaction energy of the proton we have to find out. So first of all, we have to find out that whether this reaction is possible or not, and then we will find that energy, what is the amount of energy need to be provided. So let's calculate total energy or Q value of this reaction. That will be daughter minus parent. So that will be 2 into, as we have 2 helium atom, 4 nucleons of helium atom, multiply the binding energy of helium, that is 7.06, minus that for lithium, it will be 7 times 5.60. So that will be the Q value. And here we have to multiply it by C square. And one thing I got wrong, that Q value is actually mass of parent minus mass of daughter times C square. I took it reverse. I took mass of daughter minus mass of parent. So I have to add a negative sign here. So when we solve this, what we will get? we will get, oh sorry, c square will not be there. Why? Because it is already in MEV. It is already in MEV, so we don't need to multiply it by c square. So after solving, we will get 17.28 MeV. That is option B for us. Now let's move ahead. A nuclear transformation is denoted by X and alpha 7 lithium. Which of the following nucleus is X? So basically the reaction is something like this: X and comma alpha, and we have 7 lithium. So what does this denote? It denotes that we have some element X on which we bombard a neutron and which give rise to a lithium plus alpha particle. So now let's assume mass is A and atomic number is Z, then A plus 1 is equal to 11, so A is 10, and Z plus 0 is equal to 5, so Z is 5. So that is option A. Next one, a nucleus disintegrates into two nuclear parts which have the velocity at 2:1. The ratio of their nuclear sizes will be. So they have velocity ratio is given. We know that assuming that nucleus initially at rest, so initial momentum is 0. So their final momentum should also be 0. So that will be m1 v1 plus m2 v2. So from this, I can write that m1 v1 is equal to minus m2 v2. And from this, I can write that m1 by m2 is equal to v2 by v1. And here we have a negative sign. Now I know that ratio of m1 and m2 can't be negative. So I remove the negative sign. So m1 by m2 will be equal to v2 by v1, and that will be 1 by 2. So 1 by 2. Now we have the ratio of their masses, and for nuclear, for the nucleus, we know that R is R naught times the mass of the nucleus raised to power 1 by 3. So if I compare their radiuses, then R1 by R2 will be basically equal to M1 by M2 raised to power 1 by 3. So the answer is 1 by 2 raised to power 1 by 3. So option B is the right answer. So in the next one, we have binding energy per nucleon for deuteron and helium given. If two deuteron nuclei react to form a single helium nucleus, the energy released is. So here we have two deuteron forming a helium nucleus. So let's calculate the Q value of the reaction. That will be parent minus daughter. So for parent, we have two helium, two deuteron. So twice. Each deuteron has two nucleus, and they have the energy that is 1.1 per nucleon. Minus for helium, that is 7 times 4. Yes, 7 times 4. So here Q value will come out to be minus 23.6 MeV. So this will be the amount. Here Q value is negative, so this will be the amount of energy supplied, but it is asked that amount of energy released. So we assume that there will be some misinterpretation, but energy will be 23.6. So option A will be the right answer. Now let's move to the 26. When uranium-238 originally at rest decay by emitting an alpha particle having speed u, the recoil speed of the residual nucleus is. So we have a uranium-238 and it is at rest, so velocity is 0. And then decay to alpha particle, that is 4He2 with speed u, and the remaining will be 234. And it's, I don't remember the exactly what is the Z for here. So leave it is as it is. So let's say its velocity is v because we need only mass. Why? Because we will do momentum conservation. So according to momentum conservation, initial momentum is 0, final momentum will be 4u plus 234 times v. So from this, value of V comes out to be minus of 4U divided by 234. So that is, now let me do one more thing. Sorry, this will be 234. It is asked that what is the speed. So if we have been asked that what is the velocity, then velocity should be negative. But if we have speed, now speed is normally not taken as negative. It is only taken in the form of magnitude. So if it is specifically asked as speed, then I can say 4U by 234 in positive will be the right answer. So moving to the next one. In the nuclear fusion reaction, we have this reaction. Given that repulsive potential energy between the two nuclei is 7.7 10 to the power minus 14 joule, temperature at which gases must be heated to initiate the reaction nearly is. Now, we know, we have already discussed it in the 11th class, that each degree of freedom has a half kT energy associated with it. Now, we are hitting it, so assuming that only translational modes are active, because there are vibrational modes also, rotational modes also. So we don't know that what will be the number of modes active here. So let's start with only translational modes. So if translational modes are active, then the energy of each molecule or each atom will be 3 by 2 kT, and that energy should be equal to the this repulsive energy, that is 7.7 into 10 to the power minus 14. So from this, if we solve for T temperature, that will be 7.7 10 to the power minus 14 into 2 divided by 3 into K, that is 1.38 10 to the power minus 23. And when we solve this, we will get 3.71 into 10 to the power 9. So the order will be 10 to the power 9 Kelvin. So from that, I can say option D will be right answer. Now let us assume that instead of 3, there are vibrational modes, so there are 5 modes. So if we have 5 modes, then here I will have 5. So what I can do, I have divided by 3, so I multiply it by 3 and then divide by 5 if we have 5 modes. So again I will get 9 by 5, that will be approximately 2. So that will be 2 into 10 raised to power 9, something like this. So again, I will get 10 raised to power 9 Kelvin as answer. So from that, I can safely assume that it will be the right answer. So with this, I end this video here. Hopefully, whatever we have covered up to here is helpful to you. Again, if you have any doubts, suggestion, put them in comment section. I will try to resolve them. And if you find this video useful, then press the like button, share it, subscribe to our channel, and we will meet in next video.